My name is Daniel Bregas. I'm a senior here at North Dakota State University in the Electrical Engineering Department.
My name is Christopher Larson, and I'm also a senior in the NDSU Electrical Engineering Department.
This is our device, the skin measurement device. Our group number is SD1406.
So a little intro to our device. The whole background of our device is to address people who have experienced excess skin. Now, most of these people are persons who have undergone weight loss surgery or who have lost weight during a short period of time. This can result in excess skin and can actually leave people with a worse body image than before the weight loss. The problem that our client posed to us is that currently methods are not reliable for predicting the amount of excess skin. Our requirements were to build a device that would allow us to get within 70% accuracy. The approach that we used for this was to actually measure the amount of fat underneath the skin rather than the actual surface of the skin. Our design specifications specifically were to design a device that would be able to measure the excess skin on a body. We were supposed to do this within 70% accuracy as compared to our optical phantoms, which are just silicon models with the same optical properties as fat. The device should be able to be used before and after surgery. The device should be able to be operated by a clinician with limited training, and we should also be able to map roughly of the fat thickness on a person.
All right, so just to kind of give you a basic overview of our project, here's a basic block diagram kind of breaking down our project. So when we begin our testing, we actually have 3 LED states. The first LED state is we have our array of about 5 LEDs, and the top 3 LEDs turn on, and we get a reading from our photo transistor. That's the sensor that we use to kind of pick up those light readings coming back from the fat. Now we then move on to LED state 2, get that reading, LED state 3, get that reading, and then we move from that state, we get that reading, and we also get our accelerometer reading. This gives us our position information that we're going to be using in order to kind of map where we get which fat readings. So we send all 3 of these voltages that we got from our LED states, and then we kind of put that into our fat thickness algorithm, and out of it we get our fat thickness. From our accelerometer voltages, we put that into our position algorithm, which is just a double integral, and we go ahead and get that position information. Then we take these 2 values, map them, and then we start the process over again and continue looping through and getting this information. So here's our basic schematic, and all of the circuits that we use are kind of simple. So for the first phototransistor circuit that we're using here on the edge here, what we do have is we have a 5-volt source coming down through this phototransistor. The light, depending on how much light comes through, it'll let more or less voltage basically across it. So it kind of works as an active transistor, and then when you shed a lot of light on it, it becomes super saturated. Yeah, thank you. Becomes saturated. At which point we take this voltage and then we measure it actually across a 1 mega ohm resistor. The reason we chose such a high resistance is it offers us a lot of sensitivity. Now we take that reading, we feed it directly into a instrumentation operational amplifier, and what that does is it takes our small reading and makes it large across a much larger range, so it's easier for us to pick up and see differences. Now our LED circuit is controlled via 3 PN2222 transistors, which control 3 branches of the circuit, all of which are run off a 9-volt battery. So you can see we have some current limiting resistors up in front here. In our first state we have 3 LEDs, then we have our transistor here, then we have a second state of just only 1 LED, then we have our transistor, and the last state again is just 1 LED and a transistor. Over here we have our accelerometer, which we get our information from and feed that directly. All of this information is fed into this little port, which we plug our ribbon cable, which comes out of the device and into our data acquisition card.
All right, this is our PCB design. That's printed circuit board. Here is the same circuit that Dan was talking about, but here is the physical layout. Here we have our LEDs arranged in the dimensions specified, so we know the angle that the light is coming in and can measure it. this helps us with our algorithms. Here we have the transistors, and then accelerometer and our op amp. All of this was designed to fit on a small board so that we could fit it inside of our enclosure.
Okay. You can see here, this is just a basic design. You can see you can kind of see the layout of our PCB. You can see right here we have the array of 5 LEDs, the 3 on the top, then 1 in the middle, then 1 on the bottom. And then down here is our sensor. So going through here, our ribbon cable is tying into some harnessing, which is tying into our National Instruments USB 6008 DAC card, which feeds directly into the computer, from which we can use LabVIEW software to actually perform a lot of these calculations and get a lot of these readings turned into usable information. And then this is what our final device looks like when you put everything together. Again, you can see the LED array up here, our sensor down here, and the ribbon cable coming out.
Some of the lessons learned and suggested improvements for a project was that calibration can take a long time. It's a very strenuous process. Another key factor in the success of our project was clearly identifying problems and then being able to test each of the sources of the problems individually. Some of the suggestions that we have for a possible future project would be adding a third axis or a z-axis, and then also to get human testing. Here's a quick overview of our budget. We were budgeted originally $200. We ended up coming under that. We spent $139. The total cost for our goods was $184. The gap was made up by the NDSU parts inventory.
Okay, so the basic conclusion, there are endless applications for many combinations of different technologies. You're going to find out that throughout your whole career here at the electrical engineering department, that you're going, especially for your senior design project, you're going to be relying on a lot of that past information that you learn, in your basic classes. It really all comes together here. Then we learn the importance of clear requirements and objectives that are vital to the success of the project. Having clearly stated and easy to test and attainable objectives and requirements are crucial to really getting your project to work. Making sure that you're always trying to hit those requirements is very important. And lastly, we just want to give a special thanks to Dr. Schroeder for all of his advice and guidance on our project. I know we definitely had a lot of problems along the way, so definitely he helped us out with a lot of that.